Okay, let's talk about the mean value theorem for derivatives and also Rolle's theorem. And in a minute, you'll see why I made that so small, so itty bitty. Anyway, if you need this sheet to take notes, you can go to bit.ly/MVT notes, mean value theorem notes. And there is a mean value theorem for integrals that we will learn later. That's why I put mean value theorem for derivatives. However, if you only say the mean value theorem, people will assume you're talking about the one for derivatives. The mean value theorem for antiderivatives or for integrals is often referred to as the average value theorem. But enough random talking about the mean value theorem's name. Uh, for the time being, if you go to any PDF on my Google Drive, it will display a single page. Then if you try to scroll, it zooms in and out. This should be a 2-page document. And so if you only see one page, you will need to click the download button right there. It will download to your local drive. And now you can see both pages and it scrolls as it should. So if you only see one page of the PDF when you go to that bit.ly link, then know that you can download it to see the second page. So let's talk about the mean value theorem. And we'll just start off by giving you the mathy definition, which oftentimes is very difficult to understand. So we will illustrate it graphically. But the conditions for the mean value theorem are that your function f must be continuous on the closed interval a to b and differentiable on the open interval a to b. And if that is true, then there will always be some value c on the interval a to b, such that f prime of c equals f of b minus f of a over b minus a. So there is your mathy definition. And the reason we are continuous on the closed interval and differentiable on the open. You should know that if a function is differentiable on an interval, it will therefore be continuous. So could not just say we're differentiable. And there is a case, it is possible that we could apply the mean value theorem on a function that has a cusp where we include that cusp on the left endpoint or the right endpoint and the other points over here. So in this case, we are continuous on the closed interval a to b, yet we're not differentiable at a. We must only be differentiable between the points a and b. So do not think you have to be differentiable on the closed interval. That's rare, but I wanted to point out that difference. So illustrating this graphically, we have a function here that goes from point A to point B. F of A would be the y, what in the world was that? Would be the y coordinate at A. F of B would be the y coordinate at B. And what this is saying, f prime of c means the slope of the curve, the instantaneous rate of change, the slope of a tangent at a point x equals c equals this. And you should recognize that formula as the formula for slope that you learned about 43 years ago. And if we find the slope from point A to point B, that slope would be represented by this line right here. What mean value theorem says is that some point on this interval, you must have a tangent with the exact same slope as that secant. In other words, the tangent is parallel to that secant. And as I have drawn this one, that occurs, I can drag my tangent, it occurs about right there. And so there is some point C where the tangent, the slope of the curve at that point is the same as the slope of the secant that goes from point A to point B. So there you have an illustration for the mean value theorem. Let's go ahead and knock out Rolle's theorem. And Rolle's theorem is so close to being the mean value theorem, it just adds one extra little condition. So we do have the same requirement of continuity on the closed interval a to b, differentiable on the open interval a to b. And the extra condition we apply to Rolle's theorem is that f of a must equal f of b. So everything else is the same. So Rolle's theorem is really, I'm going to come down here and go ahead and show you this part. It's really only a very specific case of the mean value theorem. So Rolle's theorem is the mean value theorem with the extra condition that f of a is equal to f of b. Well, if the mean value theorem guarantees that you have a slope, a tangent with the same slope as a slope from point A to point B, well, if f of a and f of b are the same, then the slope of that secant would be 0. And so we need, whoa, what just happened there? So Rolle's theorem is the mean value theorem with the very specific case that your f of a and f of b are the same, and therefore there must be a point on the curve where you have a horizontal tangent that is parallel to the slope of the secant, or to the secant, that connects A to B. So Rolle's theorem is a very specific case of the mean value theorem. Rolle's theorem is not mentioned specifically in the AP Calculus course description because if you know the mean value theorem, then by default you also know Rolle's theorem. So we won't mention Rolle's theorem by name very often because it is simply the mean value theorem. So let's use Rolle's theorem or the mean value theorem in a few examples. And as soon as I say we're not going to name Rolle's theorem very much, here I go naming it. All right, so determine if Rolle's theorem applies to this function. So in order for Rolle's theorem to apply, function must be continuous and differentiable, and we have a quadratic. That is a polynomial. All polynomials are always continuous and differentiable. We also need f of a to equal f of b. Now, we know that parabolas are continuous and differentiable. However, I want to state that. So f is continuous and differentiable for all real numbers. Next, I want to see, does f of a equal f of b? So f of a, f of negative 2 squared is 4. 2 times negative 2 is negative 4 minus 4. Look at all the 4s is equal to negative 4. That's another 4. Okay, let's plug in 0. F of 0 is equal to 0 squared plus 2 times 0 minus 4, and we get another negative 4. So it is true that f of 0 does equal f of negative 2. The function is continuous and differentiable. Therefore, Rolle's theorem does apply, and we now need to find the value of x on the interval 0, negative 2 such that f prime of c is equal to 0. So we will do that by simply finding the derivative. F prime of x would be 2x plus 2. We will set that equal to 0 because that's what Rolle's theorem says. Rolle's theorem says we must words are not coming out of my mouth correctly. Rolle's theorem says we must have a point where the derivative equals 0. And if you solve for x, we get x equals negative 1. I'm going to check negative 1 is indeed on the interval. It happens to be right smack dab in the middle of the interval. That does not have to be the case. That only happened here because we are looking at a quadratic. If it were a cubic function or anything else, then that likely would not have been the case. So there's a case of an example of Rolle's theorem. Let's look at the mean value theorem. So we have this function, another quadratic on the interval 0 to 2. The mean value theorem guarantees that f prime of c equals m for some c on the interval 0 to 2. Find c and m. And this problem does not ask you to confirm that mean value theorem applies. However, it is very, very, very good practice and a good habit to get into to state that your function does meet the requirements. So I'm going to go ahead and declare that f of x is indeed continuous and differentiable. And I'm going to make one tiny little tweak here. On the previous problem, I said continuous and differentiable for all real numbers, but in the context of this problem, I'm really only interested in what's happening on the interval 0 to 2. So we are continuous and differentiable on 0 to 2. Therefore, your mean value theorem says that f prime of c must equal f of b minus f of a, which are a and b are 0 and 2, over 2 minus 0. And we will solve this. I'm going to come over here on the scratch paper. I'm going to find f of 2. F of 2 is 4 times 2 squared. That would be 16 minus 5 times 2 is 10 plus 1. 16 minus 10 is 6 plus 1 is 7. F of 0 is going to be 1. And so I'm going to plug those in. So I need f prime of c to equal. F of 2 is 7 minus 1 over 2 minus 0. And my derivative, f prime of x, would be 8x minus 5. And so if I really want to appease the gods, I have declared f prime of c here. So I probably, instead of writing 8x minus 5, I'm going to write 8c minus 5 is equal to 7 minus 1 is 6 divided by 2 is 3. We will solve this equation. We get 8c is equal to 8. And when you divide by 8, you get c is 1. And so there's my value of c. The value of m is the average rate of change from A to B. So M would be 3 in this case. And once again, we just happen to get the integer, the x coordinate that is right smack dab in the middle of the interval, but do not assume that will always be the case. So let's look at two more examples, or actually it's one more example, but with 3 questions. So I guess that averages out to 2, right? I don't know. I'm just making up math here. Okay, so we have a table of values that give values of a differentiable function f. Now pay attention, that's a very important word. This is a differentiable function f. Use the data in the table to answer the 3 questions below. This is how on the AP exam and in AP free response questions particularly, we very frequently see mean value theorem or Rolle's theorem questions posed in this way with a table of values that will usually describe the function as differentiable. Every now and then they may say the function is also continuous, but you are supposed to know that if a function is differentiable, it is also continuous. And that is a very, very important declaration to make in the world of free response questions. So question A, explain why there must be an x equals a on the interval 0 to 10 such that f prime of a equals 0. Whenever you're trying to guarantee that the derivative is equal to something, I'll always start with the mean value theorem. I'm going to start with the mean value theorem. Now, in this case, we do want the derivative to equal 0, so we are looking at an instance of Rolle's theorem. However, we can just call it the mean value theorem. And the mean value theorem says that as long as your function is differentiable and continuous, then there must be a point where f prime of a is equal to 0. So let's see if we can figure out how this is going to happen. And you do need to explicitly write out that our function does satisfy the conditions for mean value theorem, which are that f of x is differentiable and continuous, but your wording is very specific here. I'm going to say f of x is differentiable. Now that's given. And because the function is differentiable, I also know it is the fact that the function is differentiable that convinces me that the function is continuous. So f is differentiable, therefore continuous. And you must word it that way in some related sense. You cannot simply say f of x is differentiable and continuous, because that doesn't convey to the reader that you understand the relationship between those two. So we have to say that the function is continuous because it is differentiable. F is differentiable, therefore it is continuous. So you have to explicitly communicate that you understand that relationship. So f is differentiable, therefore continuous. Now, if I want the slope to equal 0, I want to find 2 values of x that give you the same value of y, and that happens at 0 and 10. So what I would say now, f of 0 is equal to f of 10, which I'm going to go ahead and say they both equal 1. Therefore, f prime of a must equal 0 for some a, for some x equals a on the interval 0 to 10. You do not have to name the theorem. And as a matter of fact, I would encourage you not to name the theorem, because if you accidentally say the wrong name, that can be held against you. They do not tell you to name the theorem. They just want you to explain why this must be true. And I have now explained why this must be true. So let's look at a couple of others. Same table of values, very similar question. One difference here is I'm asking you, is there a B? The previous problem the previous problem told you to explain why it happens. Here we have to first get the yes or no out of the way. Must there be a B such that f prime of B is equal to 3/2? Again, we're trying to guarantee that the derivative is equal to a certain value. And if I'm trying to guarantee that the derivative is equal to something, I'm going to start. That says start. I'm going to start with the mean value theorem. And the mean value theorem says that as long as your function is differentiable and continuous, which this one is, and because I'm going to try to use the mean value theorem, I'm going to go ahead and declare that the function is differentiable and continuous by writing the exact same sentence I wrote earlier. And I'm going to cheat this time. There it is. F is differentiable on 0 to 10. Therefore, f is continuous on 0 to 10. Now, what I'm tasked with finding is I need to find 2 values of x where the slope between those two is equal to 3/2, because my general formula for the mean value theorem is f prime of c must equal f of b minus f of a over b minus a. And I need to find 2 points on this curve such that that will equal 3/2. That's what I'm looking for. That's what I'm looking for. I like to start with the given endpoints. However, if you look at 0 and 10, if I do f of 10 minus f of 0 over 10 minus 0, I get 1 minus 1 over 10, which is 0. It is not the 3/2 that I wanted. That does not mean that this value of b does not exist. It just means we have to fish around for it. And so I'm trying to find any 2 points on this interval, on this table, between which the slope is going to be 3/2. And if you play around with this long enough, you will find out that if I find the slope from 2 to 6, we will get 3/2. So I'm going to say, therefore, f prime of b would equal f of, and I know I said we're differentiable and continuous on 0 to 10, but we can use these points that are inside that interval, f of 6 minus f of 2 over 6 minus 2 is going to be 4 minus negative 2 over 6 minus 2. That is 6 divided by 4, which does indeed equal 3/2, and that is sufficient. We do not need to explain by the mean value theorem. We don't need to write this big, huge, conclusive sentence. We have explained that this does happen, and you do want to get in the habit of including a difference quotient in your answer, either that one or this one. Do not jump straight to f prime of b equals 6 over 4. You have to show explicitly the formula for slope being a change in y over a change in x. And one more example. Same table, everything's the same. We have the differentiable function. This time I'm asking, does f of c equal 0? This is different. I didn't say f prime, I said f. When you're trying to guarantee function values, I have snuck a different theorem in here. We're going to start with intermediate value. So we're bringing up something from the past, and the intermediate value theorem only requires continuity. They didn't tell you the function is continuous. They said the function is differentiable. So once again, I'm going to do that statement. F is differentiable on 0 to 10. Therefore, f is continuous on 0 to 10. And what I need to do for intermediate value theorem is I need to find 2 values of x that give you y coordinates that straddle a y coordinate of 0. And you can choose several different ones. I'm going to go with 0 and 2 because at 0, f of 0 is 1, f of 2 is negative 2. And if we are continuous and we go from a y coordinate of 1 to negative 2, we must cross 0 somewhere. Because I'm trying to achieve a value of 0, I want to tie this specifically to that. 1 is greater than 0, negative 2 is less than 0. Therefore, f of c is equal to 0 for some c on the interval, and I can narrow it down to 0 to 2. The question asks from 0 to 10, but because 0 to 2 is within that interval, we are okay with this. And that ended up being a little bit longer than I wanted to. Rambled too much, and I'm done.